Okay, so let's now talk about three-phase thyristor based rectifiers, right? So we have already seen single-phase thyristor rectifiers. We have also discussed about three-phase diode rectifiers. Let us see what happens in three-phase diode rectifiers if we replace those diodes by thyristors. So if you remember, in three-phase diode rectifier, we talked about a three-pole circuit, which was essentially a combination of three single phase half wave rectifiers, right? So that circuit, again, the three diodes, we can replace it with three thyristors, and that brings us to this circuit which we are going to discuss in today's video. So let us see that circuit. Let me first start by drawing that circuit. So it has three sources, and it had three diodes, and they are well clubbed to a single load. And this was the original circuit where, let's say, this is VAN, VBN, VCN, right? And this was earlier diodes, but now let us replace them with the three thyristors, so it becomes a controllable circuit instead of an uncontrollable rectifier. Let me call it as let me say TA, TB, and TC, right? All right, so let's see how would the different waveforms look like in this case. And draw the so this is VAN, VBN, and VCN, and this is where 0 to 2 pi gets completed, right? All right. Now, if this would have been a diode rectifier, right, instead of a thyristor based rectifier, then you understand that the conduction of A phase, or rather DA, the diode corresponding to A phase, would start at theta equal to 30 degrees, right? So if this would have been a diode rectifier, DA would have started conducting at 30 degrees, DB would have started conducting at 120 plus 30 degrees, and DC would start conducting at 240 plus 30 degrees, right? So 30, 30 plus 120, and 30 plus 120 plus 120. If this would have been a only diode rectifier. And therefore now here, the way we have defined alpha, which is the firing angle for the thyristor, we define with respect to these values. So now if we have thyristor A, we define alpha with respect to 30 degrees, right? And TB, thyristor B, would be fired at angle. So that means thyristor A would be fired at an angle of, so let me use other color pen. So thyristor A is, let's say, being fired at this instant. So we define this difference as alpha. So the total, so firing angle is alpha, right? And it is fired at theta equal to alpha plus 30 degrees if theta is starting from 0 here. Is that okay? So firing angle is always defined in this case with respect to the point at which diode would have, if there would have been a diode, it would have naturally started conducting, right? So therefore, if you see here, it is alpha is this difference, Right? So by default, if the question or the problem says firing angle is 10 degrees, that means the difference, the angle is, the TA is fired at 10 plus 30 degrees. Excuse me. So TA is fired at 10 plus 30 degrees, right? So that's how we define alpha in this case. So now similarly, you can see TB would be actually would be fired at, if I can show here, then B, natural firing would have happened, natural conduction would have happened here. So now it is alpha times later. So this is alpha, right? And for C, again, naturally it would have started conducting here. So if it's thyristor, it's being fired here. So each of the TA, TB, TC are at 120 degree phase shifted. So wherever TA got fired, plus 120 degree will be TB firing, and wherever TB got fired, plus 120 degrees would be TC firing. Right, so they are three separated by 120 degrees. The only thing is alpha is defined not with respect to 0 but with respect to 30 degrees. That is the only difference. If you see earlier circuits, they were all single phase circuits, so naturally diode would have started conducting at theta equal to 0, right, if the load was continuous. So therefore we always defined angle alpha with respect to theta equal to 0, but here we define alpha with respect to theta equal to 30 degrees. You can also see this, that what is happening at 30 degrees. At 30 degrees, if you see VCA is equal to 0, right? So in some ways, if you have, this is also another way of saying you define with respect to 30 degrees, or you define with respect to the zero crossing of VCA. Right, the negative zero crossing, or with respect to the zero crossing of VAC, the positive zero crossing. Okay, now let's move on. Once we have defined these firing angles alpha in this circuit, let us see how the output voltage would look like. So let us assume that we are dealing with continuous load current, right? And let us see how would the output voltage look like. So let me choose. So let's try to draw the output voltage. As we discussed before, we always start drawing from one of the trigger angles. So in this case, let us say we start drawing from this angle where TA is fired, right? Where TA, this is TB, this is TC. So immediately after TA is fired, you see that VAN is at the highest potential, highest voltage. Therefore, the anode of TA is at the highest potential among the three, and plus TA is fired, right? So what does it imply? Anyways, now TB and TC are not fired. So therefore, among these three, TA is at a highest potential, so TA will start conducting, right? And it will conduct till, it will continue to conduct till TB is fired, and then it will be VB, and it will continue to conduct till TC is fired, and then it will be TC. Right? This is how the output voltage waveform would look like in this case. Right? So now once we have drawn the output voltage waveforms, let us also try to find the average value of the output voltage. So how do we calculate the average value of the output voltage? We can calculate the average value of the output voltage by integrating. So if you see, this is 3 pulse, so the 360 degrees is divided similarly among all the 120 degrees thing. So what we'll do is we'll find an average over 120 degrees, and that would be the total average. So what we can do is we can start integrating from this point TA and go up till this point, right? And we integrate over this, and that would actually give us the answer for the average value of output voltage, right? So what is average value of output voltage? It is 1 upon 2 pi by 3, 120 degrees, integral theta going from theta equal to 30 degrees. Sorry, let me write everything in radians now. Theta going from pi by 6 plus alpha 2 theta going to pi by 6 plus alpha plus 2 pi by 3, right? And what is the value during this period that we want to integrate? What will be the output voltage? During this period, the output voltage will be equal to VAN, right? All right, now let us try to simplify this expression. Let me use the space available here to further simplify this expression. So what is VAN? We can say VAN, looking at this figure, right? We can define VAN as, let's say, VM of phase into sine of theta, right? This is VM of phase, wherein VM of phase is nothing but equal to the peak value of the line to line voltage upon √3, right? So this maybe we'll substitute towards the end, but just for information. So the phase voltage peak value is line to line peak value divided by √3. So as of now, let's substitute this first term into the above integral and try to solve that integral. So we see that V0 average is nothing but equal to 3 upon 2 pi integral going from pi by 6 to alpha to pi by 6 plus 2 pi by 3 plus alpha, and this is nothing but VM phase into sine of theta d theta. So you can further rewrite as 3 upon 2 pi VM phase integral of sine is cos of minus cos of theta, so cos of pi by 6 plus alpha minus cos of pi by 6 plus alpha plus 2 pi by 3, right? Further we can rewrite it as 3m phase upon 2 pi into cos A minus cos B is minus 2 times sine of A plus B by 2, which would be pi by 6 plus alpha plus pi by 3, right, into sine of A minus B by 2, which is going to be minus pi by 3, right? You can further simplify it. We'll get 3 times VM phase upon pi upon 2 pi into minus 2 into sine of 90 plus alpha cos of alpha into sine of minus pi by 3 or minus 60 degrees, which is going to be minus √3 by 2, right? So what we'll get is 3√3 VM phase upon 2 pi cos of alpha, which you can also rewrite it as 3 VM line to line cos of alpha by 2 pi, right? So this is the average output voltage as a function of alpha in case of 3-phase 3-pulse thyristor based rectifier. Obviously, if you put alpha equal to 0, that means it behaves as a diode rectifier. You get an average value for a diode rectifier case. Okay, now this part is clear. Now let us also give a little bit of thought that what is the maximum value of alpha that we can keep in this circuit, right? What is the maximum alpha that you can keep in this circuit? So let us see. Let me use, okay, let us see till where can I keep alpha. For example, I can certainly take alpha as of now. If you see in this figure, alpha is shown as very small value. I can certainly increase alpha and bring it to, let's say, 60 degrees. So alpha will be equal to 30 here, theta would be equal to 60. So let me only talk in terms of alpha. So I can bring alpha to 30 degrees, no problem. I can bring alpha to 60 degrees, no problem. I can bring alpha to 90 degrees, no problem, right? I can bring alpha to 120 degrees, right? No problem. Can I bring alpha to 120 plus 30, that is 150 degrees? Can I bring alpha here? What will happen if I bring alpha here? Imagine that before A phase, C phase was conducting. At this point, I am giving a trigger pulse to A phase. Now, will A phase conduct? Yes, A phase will conduct because A phase voltage is greater than C phase voltage. So I can bring it to 150 degrees also, no problem. Actually, I can bring it till this point, which is 180 degrees. Because after this, if already C phase is conducting and I try to trigger A phase, then A phase will not even start because A phase voltage will become less than C phase, right? So I can, in this circuit, I can keep alpha anywhere between 0 to 2 pi, right? So I can keep alpha between between 0 to pi, right? So alpha range is 0 to pi. Right, just check this one. If there is any further confusion, let me know. I'll be happy to discuss it again. And yeah. Okay, so this was half-wave kind of configuration. You understand the limitation, which is the same as we discussed before, that the input current, if you see from each of these phases, they are going to be a DC current. They're not going to be, they will have a DC component, and which is not good for the system. And that is the reason that for understanding this circuit is good, but we do not really use it for practical application. So what we'll do is let us move on to another circuit, which is also a three-phase circuit, three-phase full bridge or fully controlled bridge.